Today we're going to talk about trying to prove triangles congruent. We mentioned before that two geometric figures are congruent if all their sides and all their angles are congruent. If corresponding sides, corresponding angles are all congruent. Something interesting happens with triangles, and it's due to something called triangle rigidity, which basically says that given certain side lengths and angle measures, given 3 side lengths or given 2 side lengths and an angle measure or some other parameters, there are only so many ways you can make a different triangle. For instance, if I asked you to make a triangle that had side lengths of 3 inches, 4 inches, and 5 inches, I could ask 1,000 people, and 1,000 triangles would be created, and all 1,000 triangles would be exactly the same. They would all be right triangles, where 5 obviously would be the hypotenuse. And that's because of this triangle rigidity. You can't make a triangle with side lengths 3, 4, 5 any other way other than a right triangle. So because of that, we don't necessarily have to know that all sides and all angles are congruent in order to prove that two triangles are congruent. It's enough, for instance, to just know that all 3 sides are congruent. And so we get to our first sort of shortcut in proving two triangles congruent. And that's the side postulate, which says that if the 3 sides of one triangle are congruent to the 3 sides of a second triangle, then the two triangles are going to be congruent. We don't have to know that the angles are congruent to each other. We don't have to go measure the angles. We can just find the length of the sides and make sure that all the corresponding sides are the same. Okay? And so we can do that through some algebra or in the using some geometry theory in a 2-column proof. We can do that as well. So for instance, if we got these 2 triangles here, again, we don't have to know anything about the angles. Triangle ABC, triangle EGF, we don't know anything about the angle measures, but somehow, some way, we have managed to show that all 3 sides of each are the same. Corresponding sides are the same. So, how do we know that these 2 triangles are congruent? Well, first of all, we have to be able to write a congruence statement for these guys. And so in order to do that, to say that triangle this is congruent to triangle that, you'd have to make sure that order matters, and that we make sure we match up corresponding parts. So here we would have to say triangle ABC is congruent to triangle FEG, and it has to be written this way. It has to be written this way. Now, you can reorder ABC and call it triangle BAC or CAB or CBA, but then the F, the E, and the G would have to move around as well. So bottom line is, we would have to make sure that side AB matches up with side EF. And so side AB and side EF, they're the first 2 letters there, so that's good. And then we have to make sure that side BC matches up with side EG. And they do, the last 2 letters there, and so on and so forth. Again, the idea is to be able to write your congruent statement so that even if you didn't have the picture, you would know what parts would be congruent. Okay? All right, so order matters. So we've got to make sure we're naming these guys correctly. So some examples here. Decide whether the congruence statement is true and explain your reasoning. Okay? Well, first off, in these 2 triangles here, we would know by reflexive that these sides are congruent, but all we got to do is check to make sure that the order is fine. So according to this congruent statement, IH and JH are congruent. IH is here, JH is here, and those are not sides that are congruent. So this is not true, and that's why. IH is not congruent to JH. Okay? Here, we'd have to check the sides here as well. So LP would need to be congruent to PL. Well, sure, LP and PL are those sharing sides, and they're going to be congruent to each other. Then PS and LN would have to be congruent. PS and LN, and they are. They're the ones that are marked congruent. And then last but not least, LS and PN would need to be congruent, and they are. And so, yes, this is a true statement, and it's because, I don't know, the congruent statement is written correctly, or the corresponding parts are matching. Okay, something to that extent. Okay? And that's what you're looking for. So here in number 3, AC and BD would have to be your congruent parts, AC and BD, and they're not. And it's because AC is not congruent to BD. And then the same thing over here. We're going to make sure these guys match up. ST and UT, yes, those are good. TV and TV, yes, those are good. And then SV and UV, and yes, those are good. Okay? So that's what we wanted. That's what we're looking at there. Just making sure that we're writing the congruent statement correctly. Okay? Now, showing that two triangles are congruent, verifying that two triangles are congruent. There are a couple of different ways to do this. One way is to take the two triangles and put them in the coordinate plane so that the vertices match up to coordinates. Okay? If we do that, then we have to find some way to show that each corresponding sides are congruent. If they're congruent, they're going to have the same length. So how do you find length when these sides are in the coordinate plane? Well, quite simply, we would use the distance formula. We would have to find the distance in the distance formula, which says subtract the x's and square them, subtract the y's and square them, and then add them together and square root. So we have to check all the distance formulas. Now, for horizontal and vertical lines, you don't have to use the distance formula. You can just count the lines, right? And here, each line is scaled in 2, so each line represents 2. So, for example, JL, the length of JL would just be 2, 4, 6. So JL is 6. JK would just be 1, 2, 3. Okay, and so on and so forth. And I'll leave that for you guys to verify, but you'd need to go find the length of all the sides and make sure that all 3 sides are the same. Here it shows KJ and SR are both 3, JL and RT are both 6, and LK and TS are both 3 square root of 5 by the time you're done reducing or simplifying the radical in your distance formula. Unfortunately, you'd have to use the distance formula for JK and TS. Okay? All right, so that's it there in the coordinate plane. There's another way to show that these two triangles are congruent, and we can put that in form of a geometric theory proof or a 2-column proof. The coordinate proof is more about algebra. A 2-column proof is more about using what you know about geometry rules. Okay? So, here we go. We've got this diagram. We've got some given information. We want to prove these two triangles are congruent. So, we always put in our given first. And again, I like to list all my givens together. So statement 1 would be my givens. And if the picture wasn't marked already, what I would tell you is once we've said that things are congruent in our picture, we can go, once we've said that two things are congruent in our proof, we can go mark our picture. So A, B, and C, D are congruent here and here. And B, C, and D, A are congruent here and here. Okay? Now, what next? Well, I've said before, I love it when two triangles share sides. And these two triangles are sharing this side right here. If we were to pull these two triangles apart, they would both have side AC as one of their sides. So since that's the case, we can write in here that AC is congruent to AC because of reflexive. Of course, it's going to be congruent to itself. So now AC being congruent to AC provides our third set of congruent sides. All sets of our sides are marked congruent. So we're done. We've shown we can now use side, side, side to show that triangle ABC is congruent to triangle CDA. And so that's how we're going to use the side, side, side congruence theorem, actually congruence postulate, in a two-column proof. All right? Got another proof here for you. A little bit more involved, but not a lot. So we have this diagram over here. We've got two triangles, actually three triangles in the picture, but two that we're going to prove congruent. WXZ is here, and YXZ is here. Okay, so we do have some given information. WX and YX are congruent because it was given to us. At this point, we would go mark our picture. And then we were also given that Z is the midpoint of WY. Nothing to mark in the picture here yet. We haven't said in this statement Z is the midpoint of WY, we haven't said that anything is congruent. But because Z is the midpoint of WY, we are going to know that WZ and YZ are congruent, and that's by the definition of midpoint. So then we would have our picture marked like this. Again, I love it when two triangles share sides, because if I were to split those two triangles up, they would both use the segment XZ as a side. And so, of course, XZ is going to be congruent to itself. And so the reflexive property says that XZ is congruent to XZ, and then we'd have these guys marked congruent, and then this congruent to itself. And so now we've got side, side, side marked. So we can say that our two triangles are congruent because of the side, side, side congruence postulate. Okay? So how we're going to use side, side, side. We just got to make sure that the three sides are congruent to the three sides in each triangle any way we possibly can that makes sense, using geometric rules and whatnot. Okay? All right. Moving on. Proven triangles congruent by using side, angle, side, and hypotenuse leg. SAS and HL is what those SAS and HL stand for. First of all, side, angle, side, or uses what we call an included angle. And what we ought to add in here is exactly what in the world an included angle is. Okay? And an included angle is an angle. So an included angle is the angle between two given sides. Or an angle that uses two given sides to form it, right? So in other words, use the diagram to name the included angle between the given pair of sides. We need to be able to pick out included angles. AB is here, and BC is here. And so the included angle, the angle that uses the two given sides, would just be angle ABC. Okay? That's what we mean by the included angle. Or if we're talking about side BC and side CD, in the case of number 2 here, then angle BCD, or angle C, if you wanted to do that. You could do that since C is by itself, is the angle that uses these two sides, use these two segments as its sides. Okay? So on and so forth. AB and BD, then the included angle would be simply angle ABD. Got the pattern? Okay. Try the next 3 on your own. Try to find the included angle, and I'll let you know what those angles should be. Okay, in number 4, the included angle is going to be angle ADB. In number 5, the included angle is going to be DAB. And in number 6, the included angle is CDB. So it's the angle sitting in between two given sides. And again, we really need to be able to pick out included angles. Okay? Some other things we need to understand before we get into these two shortcuts. One, in a right triangle, we've talked about this already. The sides adjacent to the right angle, or the sides that are perpendicular in a right triangle, are called legs, and the side opposite the right angle is called the hypotenuse. Okay, we need to keep that in mind. Okay, again, we've talked about this before. There are your legs and your hypotenuse. Okay, that leads us to some theorems. The first one, the hypotenuse leg congruence theorem. If the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of a second right triangle, then the two triangles are congruent. So we even need less information for a right triangle. We don't even need 3 parts. We could just use 2 parts, the hypotenuse and the leg. Of course, they have to both be right triangles, so they both have to have a hypotenuse and a leg. And then we have to show that a leg and the hypotenuse are congruent to each other. Okay? So the right angles would be congruent to each other also. So you're still basically using 3 parts, but it's less to show if we know the two triangles are right triangles. Okay? Now, getting away from specific right triangles, in just a second we'll talk about the other theorem. But here's what we're talking about, right? So these two right triangles, we can use hypotenuse, leg, hypotenuse, leg. So all we would need are these 2 parts congruent. Or we could go use the other leg, hypotenuse, leg, and then those 2 right triangles would be congruent. We don't need all 3 sides. We just need 2 as long as one of them is a hypotenuse. Okay? And so these 2 triangles, triangle ABC is congruent to triangle DFE by hypotenuse leg congruence. And again, you would not need all 3 sides. So you can even hopefully be able to take one of these legs out. Okay? The other postulate is the side angle side congruence postulate. It says if 2 sides in the included angle of one triangle are congruent to 2 sides in the included angle of a second triangle, then the 2 triangles are congruent. It would look something like this. 2 sides, here and here, and then here and here are congruent. The angle that we can use to prove these 2 triangles congruent has to be the included angle. The included angle of those sides that are congruent already. In other words, it would have to be this angle and this angle. If we're going to use these 2 sets of sides, it would have to be these angles that are congruent so that we have side, angle, side. Not only does the order in which you write your congruence statement matter, but the order in which your parts are congruent matters as well. So the angles have to be in between your 2 congruent sides. They have to be. Okay? And if that's the case, then with 2 side lengths and an angle measure in between those 2 side lengths, you can only make one type of triangle, and that's why all those triangles would be congruent. Okay, that's why we can use side, angle, side as your reason for making those 2 triangles congruent. All right. So here, as long as the angle that's congruent is in between your 2 sides, then we can say that triangle ABC is congruent to triangle FED by side, angle, side. Okay? And again, if you get lost, use the name of the postulate. SAS suggests that the angle that's congruent is in between your 2 sides. It has to be. Okay? Side, side, sides, no problem. Just all 3 sides congruent to all 3 sides. Hypotenuse leg tells you what to go look for also. If you're going to use hypotenuse leg, you've got to have a hypotenuse congruent and a leg congruent. Okay? All right. Seeing if we have enough information to make these 2 go, to use these 2 theorems to say that our triangles are congruent. So decide whether enough information is given to prove the triangles are congruent. If there is enough information, we need to write the postulate, the theorem that we would use. So here, if we want to try to prove triangle ABC is congruent to triangle DEF, would we have enough information? So those 2 outside triangles. Well, right now we've got this side and this side congruent, and this side congruent, And then we've got the angles in between them marked congruent. So yes, there is enough information, and we could use side, angle, side to do it. The angles in between the two congruent sides. Okay? So no problem there. And number 2, do we have enough information? Think about that for a second. Got to be able to find the hypotenuse. In triangle MNO, it's a right triangle because there's a right angle. This is the hypotenuse. In triangle RON, it's a right triangle because it has a right angle, and so there's the hypotenuse. So the hypotenuses of both triangles are congruent. What we need now is just one leg. Remember, a leg is either of the other two sides. And because they share NO by reflexive, that side is going to be congruent to itself. And so, yes, we have enough information, and we can use hypotenuse leg to prove it. Okay? Hypotenuse leg. Now the last one. I've got this side congruent to that side, which means I don't have any sides congruent given to me between these two triangles, ABC and ADC. Well, except for the reflexive one, right? AC congruent to AC. But that's it. I would need to know that this side was congruent to this side, let's say, and this side was congruent to that side, let's say. Then we could use side, angle, side, but we don't know that. So no, there's not enough information here. It's not a right triangle. These two are not right triangles, so we can't even use hypotenuse leg. Okay, this is not enough information. All right, so hopefully we're familiar with what parts we're looking for, where they have to sit. So far we've got side, 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 that's no problem. 3 sides congruent to 3 sides. We've got side, angle, side, which means that 2 sets of sides need to be congruent between the 2 triangles, and the angle in between them needs to be congruent. Then we got hypotenuse leg, which says that the hypotenuses and a set of legs need to be congruent between our 2 right triangles. Okay? Now, can we apply that into a 2-column, can we apply that to 2-column proofs? And if so, how can we? So the first proof here, segment OM is perpendicular to segment LN. And then we're given that ML is congruent to MN, and we want to prove triangle OML is congruent to triangle OMN. Okay? We need to make sure we're very aware of which 2 triangles we want to prove congruent. So, if it were me, I would list all of my givens at once, but there are varying ways that you can write a 2-column proof. This one just uses the first given, so OM and LN are perpendicular. If they are, then we would know that angle OML and angle OMN are right angles, and we need to include that step. Okay? We need to include that step. And the reason why we could write this, the reason why we get to use this, is if 2 lines are perpendicular, then they form 4 right angles. And that's true. I would even be okay if you just wrote the fact that we were using the definition of perpendicular lines. Because the definition of perpendicular lines tells us that as well. What was written here originally was the theorem that we had towards the end of chapter 3, which says if 2 lines are perpendicular, then they form 4 right angles. But the definition of perpendicular lines is that as well, the 2 lines that intersect to form right angles. So either one, I think, would be fine. Okay? Now, because angle OML and angle OMN are right angles, that means that angle OML and angle OMN are congruent, and that's because of the right angle congruence theorem. All right angles are congruent. Okay? the right angle congruence theorem. All right? Now, so what that means is we've got a pair of congruent angles here, and when we write in our next given, which is here, ML and MN are congruent, now we've got a pair of sides that are congruent. Okay? Now, we do have two right triangles, and we could use hypotenuse leg to prove the two triangles congruent if we could somehow make the hypotenuses congruent, OL and ON. So unfortunately, we don't have any reason to do that yet. But what we do see is that these two triangles share side OM. And so I love it when two triangles share sides because we get a free congruent part by using reflexive. So OM is congruent to OM, and so what we see now is that these angles are congruent, and that side is congruent to itself. And so now we've got two sets of sides that are congruent and an angle in between them. And so now we can use SAS congruence postulate to say that those two triangles are congruent, making sure that we write our congruent statement correctly. Of course, if you ever need help, it's usually sitting right up here in your prove statement. Okay? So an example of using side angle side. Now, another proof. Complete the proof. And I'm going to give you about a 5-second head start here to let you start writing this. If you want to pause the video and try to write it out yourself, and then start the video again and check your answer, that would be even better. Okay, so go ahead and give it a shot. Okay? All right, so here we go. B is the midpoint of AE. That's part of our given. So is B is the midpoint of CD, and so we could keep that in mind as well. So the first statement, B is the midpoint of AE, that's going to be given. Given. Didn't quite come through. All right, because B is the midpoint of AE, we know that AB is congruent to EB. That's by the definition of midpoint. So once we've set it in our proof, AB and EB are congruent, we can go mark it in our picture. Okay, good. We've got a set of parts marked congruent between our two triangles. So let's move on and see if we can't get more parts. Well, B is the midpoint of CD is also a given. Right? So if that's the case, if it's a midpoint of CD as well, then we know that CB and DB are congruent by definition of midpoint. So now these guys are going to be congruent. Okay, good. We're 2/3 of the way there, making these two triangles congruent. Well, what's left? If you look, again, I said before, if you can pick out your angle relationships, then life gets a little bit easier. But if you look at these two angles right here, they form that X, they're back to back, and so they're vertical angles, and if they're vertical angles, they are automatically congruent by that vertical angles theorem. So now we would have this guy congruent to this guy, this side congruent to this side, and now these vertical angles are congruent. And now you've got side angle side. Two sides, two sets of sides congruent, and a set of angles in between them congruent. And so the two triangles are congruent by the side angle side congruence theorem. Okay? So just, again, some more examples on what you can look for and how to make side angle side happen. Okay? Hypotenuse leg isn't any more complicated. All you'd have to do is verify that you have some right angles in your two triangles, and then, again, just through writing what you know, try to make the hypotenuse in one of the legs congruent. Then you can use hypotenuse leg. All right? That's it. Homework's in Canvas. We'll see you next time.